Hello, in this video we will investigate the difference between classical hypothesis testing that you have probably learned at your bachelor statistical course and hypothesis testing for specification test when we are doing modeling. There are subtle differences that I would like to discuss in this video. So classical hypothesis testing amounts to pose a null hypothesis, which is simple and which is supposed to contradict a theoretical assumption. An example that was used by Fisher, the statistician who introduced hypothesis testing, is a context of a lady testing cups of tea. So in this case, the theory is that a lady is able to tell if the milk has been poured before or after the tea in a cup. This is what she claimed. This is the theoretical assumption. Now, the simple hypothesis contradicting this simple assumption is that the outcome of the test is purely random. So whenever she says that the milk has been poured before or after, is the result of a purely random decision. This is H0. In the context of specification testing, we also have the fact that the null hypothesis is a simple hypothesis contradicting a theoretical assumption. But in this case, we are testing if an explanatory variable explains the choice behavior or not. So to make the parallel with the lady testing example from classical hypothesis testing, here our theoretical assumption is that a variable explains the choice behavior. Therefore, the null hypothesis that we would like to test is contradicting this theory. H0 is that the coefficient of the variable is 0, so that the variable does not explain the behavior. When you do hypothesis testing, you always make errors. And these errors are of two types. They are usually called type 1 error and type 2 error. A type 1 error occurs when you reject the null hypothesis, but it happens to be actually true. Symmetrically, the type 2 error is when you decide to accept the null hypothesis, when in reality this hypothesis is false. What does it mean in the context of specification testing? The type 1 error, when you reject the hypothesis, means that you will include an irrelevant variable. So you will keep in the model a variable which in reality does not explain anything about the behavior. For a type 2 error, because you accept the null hypothesis, it means that you accept the fact that the variable does not play any role, you remove the variable from the model. But because H0 is false, this variable in reality plays a role and explains the behavior. So the outcome of this is that you will omit an important variable in the model. What is the impact of this? A type 1 error, so if you include a variable which is irrelevant, well, basically you will lose statistical efficiency. It means that the estimates of your parameters will be less precise. A type 2 error, because you omit a relevant variable, then you have a specification error. And actually this happens to be more severe because most of the theory, the statistical theory in econometrics, assumes that the specification of the model is right so that you can make some statistical test and statistical analysis on the estimated parameters. So let's look at the impact of the error in terms of cost, let's say an abstract cost that would represent the impact of the error. Let's call C1 the cost or the impact of a type 1 error, and let's call C2 the cost of a type 2 error. And actually, this cost is way higher than the cost of a type 1 error. So it's much more severe to do a specification error than to include an irrelevant variable and to lose efficiency. And this is one of the major differences with classical hypothesis testing, because usually in classical hypothesis testing, both types of errors have almost the same impact. So let's calculate the impact of an error. So first, let's calculate the probability of an error. So the probability to make a type 1 error is equal to the probability that we reject the null hypothesis, given that the hypothesis is true, times the probability that H0 is true. In hypothesis testing, it's common to denote the probability that H0 is rejected given that H0 is true using the notation alpha. And let's call lambda the probability that H0 is true. Now we can do the same for the probability of a type 2 error. So the probability that H0 is accepted and H0 is false is equal to the probability that H0 is accepted given that H0 is false times the probability that H0 is false. The first probability is usually denoted by beta in hypothesis testing, and the probability that H0 is false is 1 minus lambda. So given that we have these probabilities of errors, we can now calculate the expected cost of making an error. So this expected cost is the sum of the expected cost of making a type 1 error, which is the probability that it occurs, times the cost of making a type 1 error that we denoted by C1, plus the same for type 2 error. So the probability of type 2 times the cost of a type 2 error. Now we use the quantities that we have calculated above. So the probability of type 1 error is alpha lambda times C1. And the probability of a type 2 error is beta times 1 minus lambda. And now we have C2. In classical hypothesis testing, lambda is close to 1. So usually H0 is a hypothesis that we really believe in. And as I said before, the cost or the impact of making a type 1 or type 2 error is basically the same. So it means that to minimize the expected cost, it's custom to take alpha, which is low. In practice, it's usually taken to be 5% or 1%. So we prefer small alphas. In specification testing, the situation is slightly different. First, we have no strong a priori knowledge about the correctness of the null hypothesis. We are not sure if this variable is actually playing an important role or not in the behavior. So let's say that in this case, lambda is 50-50. It may be true, it may not be true, we don't know. But as we discussed before, in this context, the cost of a type 2 error is way larger than the cost of a type 1 error. Therefore, it's recommended to use a larger alpha in this context. So using alpha equals 5%, like it is commonly used for hypothesis testing, may be too strong. And we want to use a larger alpha to avoid the fact that the type 2 error may have a big influence on the cost or the impact on the modeling scheme. So now I recommend you to do some practical tests in order to remember and to get more familiar with the concept of hypothesis testing. And then what we will do is that we will go more specifically into the testings and into the tests that we will apply for the discrete choice models.